Here we'll apply concepts of distance and displacement to a two-dimensional situation. The axes of the graph at the right represent two different dimensions of position in meters. It's a top-down view, so the horizontal axis represents the x dimension, and the vertical axis represents the y dimension, but both of these axes are on the ground. Let's say that a person completely walks around the perimeter of a rectangle and ends up in the same position that he started in. Find the total distance traveled in this situation. So distance can be given the letter d or s. And what we want to do here is we want to find the sum of the distances. Now in summation notation, one thing we can do is we can have a counter variable. The counter is going to count from 1 to 4. The first number is the starting point of the count. The number below is the start of the counting, and the number above is the ending point of the count. So we're going to have 4 things that we add up. And we're going to add up s with a little subscript of the counting variable k. But what does it really amount to in calculation? We're going to add s1 plus s2 plus s3 plus s4. Count all the way from 1 to 4. Now the first distance here will be represented by the length of this vector. Second distance can be the next vector in the sequence. Then we can have S3 and finally S4. So let's get those distances. So the distance for the first movement is about 3 meters. The next one is 2 meters. Then we have another 3 meters. And finally, just 2 more meters. This gives us a total of 10 meters. And that is what we can refer to as S total. Now remember that with distance, the direction we're walking doesn't matter. All that matters is that we're traveling, and we want to keep track of how far we've traveled. Next, what we'll look at is two-dimensional displacement. But with displacement, direction does matter. Now it's going to be helpful to analyze two-dimensional situations by breaking vectors into horizontal and vertical components. Luckily, these vectors are aligned with the x and y directions. So we don't have an unusual direction vector such as something like this. This is going to make our analysis a little bit easier. So delta x1 represents the change in x for the first leg, and delta y1 represents the change in y for that same movement. The delta x here is going to be final minus initial. So if we do x final minus x initial, it'll be 4 minus 1, which gives us a delta x of 3 meters. But when it comes to the delta y for that same vector, we're not going up nor down. We're going to the right. For that reason, the delta y will actually be 0. And now we're done analyzing the first vector. We want to look at the next change in position that was made. So that would be this vector here that goes up. So the delta x for a vector which points directly up is actually 0. And the reason why is you're not going to the right, you're not going left, you're just going up. And so our delta y will actually be 2 meters. Now let's analyze the third vector. The third vector points to the left. So if we do final minus initial, it'll be 1 minus 4. But that takes us to a negative 3. And when we're doing displacement, the negatives matter. So we want to keep track of that. Also, we're not going up nor down, so the delta y will be 0. There's one more vector, one more change in position to consider. We're going down 2 units, so we'll have a delta x of 0 and a delta y of negative 2. Now what we'd like to do is find the total displacement of the person from start to finish. So what we'll do is we'll sum the delta x's separately from the delta y's, and that's common in two-dimensional motion. The different dimensions are independent of each other, so we just focus on one at a time. So our delta x total is going to be 3 plus 0 plus negative 3 plus 0. That's a displacement of 0 in the x direction. And that should make sense because the final x is 1 and the initial x is 1, 2. So even though they moved around this rectangle, they didn't ultimately change their final position relative to their initial position. And when it comes to the y, the final y is 2 and the initial y is 2 as well. 0 plus 2 plus 0 minus 2 makes 0. Alright, that's one way to describe a two-dimensional displacement, is by separating the components. Now we want to express it using what's called component form and what's called vector form. So with component form, we'll use these angled brackets here, and we just want to put in our delta x total in the first spot and then put our delta y total in the second spot. It's one way of expressing a vector. It's a little different from coordinate pair because it's not just a location in the two-dimensional plane. It is a vector, but this vector has a magnitude of 0. Now we'll try ij notation, which is vector form. That's where we separate the I and j from each other, attaching the delta x to the I and the delta y to the j. Both of these say the same thing. It tells us that there was no overall displacement for this man.